Welcome back. In this part of the lecture, we will continue with transformation related with intermolecular forces. Even though we haven't discussed intermolecular forces on detail yet. So what we're going to see on this part is what evaporation and condensation are in terms of what's happening with the molecules. So let's begin with this question. Why does a glass of water evaporate more slowly in the glass than if you spill the same amount of water on a table? So let's visualize that. I have a glass of water. And I have a table. Where the glass of water have been placed. But it spills, so the water goes over the table. And the question is, why does the glass of water evaporate more slowly in the glass here than here? To be able to answer that question properly, we have to define what evaporate means. And evaporates, and you will say, I know that, evaporates means going from liquid to gas. Okay, that's good. Well, that can also be boiling, so which is which? What's the difference? So let's look at evaporate in terms of the molecules. So we got the glass of water. And as you already know, the water molecules are going to be attracted to each other by intermolecular forces. And they're going to be some on the surface, creating the surface tension that we discussed before, and some at the bottom or the interior. And we know that the ones on the interior have more intermolecular forces acting on them, and the ones on the surface only have the intermolecular forces related to the molecules below them. And that continues that way. So what's happening here? If you remember earlier on the course, we said that matter is made out of particles, and the particles are always moving. So these particles are kind of moving on random directions. This is a liquid, so they're not moving that fast. They're just moving slowly, kind of vibrating and undulating from side to side. But every so often, some of them can be moving to the bottom. They can be moving to the side. So they're moving randomly on every direction, like gas molecules, but restricted by the intermolecular forces. And like on gas molecules, the ones on top may be moving away. So if they're moving away, they will no longer be feeling the intermolecular forces from other molecules, and they will be part of the gas phase. So that's what evaporation means. When the molecules can overcome the intermolecular forces, and because they're moving by pure chance, they move away from all other molecules, becoming part of the gas phase. So that's what vaporization is. How is vaporization different from boiling? During vaporization, only the ones on top are the ones that have the possibility of doing that. During boiling, it happens also on the inside. The boiling temperature is higher, so they're moving faster, so they're separating faster from each other, and they allow the space for bubbles to form. So that's when you start seeing bubbles forming at the bottom or the inside of the water and not just on top. So going back to vaporization, so it's just the movement of the molecules from the liquid phase to the vapor phase, because randomly, by pure chance, they move away from the other molecules. The higher the temperature, the faster the molecules are going to move, so they're going to vaporize faster. But that's not what we have here. What we have here, it doesn't mention temperature, so we're assuming the temperature is the same for all of them. The only difference is that on the glass of water, you have a given surface. So remember, vaporization is the ones on the surface only. The ones at the bottom do not have enough energy until they reach boiling to vaporize. So the moment you spill it over the table, now you are exposing more molecules to the surface. The surface area is bigger, so more molecules have the possibility, remember, just pure chance of moving away from the others. And therefore, vaporization rate begins. Something else I can mention now, we're going to talk about it later, I can mention now that these molecules on the gas phase, they do not stop moving, they continue moving, different directions, and some of them are going to come back and hit the surface. And when they hit the surface, that's a force. And you learn on the past chapter that any particle hitting a wall, on this case the surface, that's pressure. So they put pressure on the surface of the liquid. That pressure or that force coming back and hitting the surface, that's what we're gonna call vapor pressure, because it's pressure that is being put in there by the molecules on the vapor or the gas phase. So that's how we can explain that the glass of water evaporates lower than the water that has been spilled on the table, because you increase the surface area, and since vaporization depends on the molecules on the surface escaping, that increases the possibility of that happening. And I already told you, if you increase the temperature, the molecules will move faster, so that possibility will also increase. So let's see another concept. What is the boiling point of a liquid? What is the normal boiling point? Like I told you before, on the glass of water, you're going to have the molecules there. We saw on the previous recording that the ones on the inside, they are affected by more intermolecular forces from all directions. The ones on the surface do not have any intermolecular force acting on them coming from the top, because they are the top, right? So vaporization is going to be the surface molecules escaping and creating the vapor pressure. Boiling point refers when every single molecule have enough energy to escape. And as the temperature increases all the way to the boiling point, the particles are going to become more separate because they're moving faster. And that space that they live in between, that's what you see as a bubble. And as they move over, all of them moving now, because all of them have the energy to do that, that space in between where there's nothing, that's what you see as a bubble coming out. So at the boiling point, every single molecule have the energy necessary to be able to escape. And they can escape from the bottom, creating the bubble as they come out, or they can just go from the top where you see the bubbles just popping at the top. And what is the normal boiling point? Well, remember, these molecules are escaping, right? But there's air over here made out of molecules also. And this air continues all the way up till the edge of the atmosphere. So that's why we say this is one atmosphere. So these molecules from the water, we have to push those molecules out of the way to be able to escape. So when the molecules have the necessary energy to push out the molecules of other gases, air, and so on that are in top of them, that's what we call that is happening, is boiling, and is happening at 1 atmosphere. So normal boiling point is nothing more than the temperature at which all the molecules have the necessary energy at 1 atmosphere to be able to escape. So boiling point is going to be the temperature at which the molecule have enough energy to escape. If it happens to be at 1 atmosphere, then we call it normal boiling point. So for example, if I have water on a vacuum, then it's not going to be 1 atmosphere, but the boiling point is still going to be the temperature at which the molecule have the energy to be able to escape at whatever pressure. If it happens to be 1 atmosphere, then we call it the normal boiling point, because the normal thing on this planet is 1 atmosphere. So one more, explain the difference between evaporation below the boiling point for a liquid and evaporation at the boiling point. And I just told you. The evaporation below the boiling point only happens with the molecules on the surface. The evaporation at the boiling point happens with all the molecules, even the ones that are at the bottom. All of them have the energy to escape. And that's why you see the bubble going up the water until it escapes. Another concept. What is vapor pressure? I already told you that. Let's review it. As the molecules from the surface escape, some of them, just by pure chance, are going to come back and hit the surface. That pressure, that force that is being put by that molecule that is moving down, that's what we call the vapor pressure. How does it depend on temperature? The higher the temperature, the faster the molecules are going to escape. And the more molecules escape, more molecules are going to be putting pressure back in, so the vapor pressure also increases. What about intermolecular forces? If I have my molecules in there, let's say one like that, and one like this, and the color is going to represent the intermolecular force. This one have a very strong intermolecular force keeping them together, while this one have a smaller intermolecular force. So the stronger the intermolecular force, the harder it's going to be for those molecules to break apart from the other ones. So the stronger the intermolecular force, the lower the amount of molecules escaping, and the lower the amount of molecules hitting the surface. So the stronger the intermolecular force, the lower the vapor pressure is going to be. The weaker the intermolecular force, it's easier for them to escape from one another, and more of them will come back and hit the surface, so higher vapor pressure. And to close this part, and I know I'm speaking a lot more than usual, what is condensation? The same way these molecules escape because they break the intermolecular force, if the molecules that have escaped that are moving as fast as when they escape because of the energy that they have, if by any chance the temperature goes down, they're gonna slow down. So their speed is going to decrease, the kinetic energy. So at lower temperature, the kinetic energy is going to be slower. And when the kinetic energy is lower, they move slower. So if I have a molecule that is partially positive, partially negative, and another molecule that is partially negative, partially positive, and this is going very fast, and this is going very fast, when they go by, this partially positive will not have time to sense and interact with that partially negative, and they will keep going. However, if they happen to be going slower, they're going to have time to sense each other, and that intermolecular forces will grab, and they will get stuck. Partially positive attracts partially negative. As they slow more and more, other molecules will start attaching to it. So as long as they're on the proper orientation, they will start congregating, and it's going to go from gas to liquid. So condensation is the opposite of vaporization, and it's because on vaporization, for them to escape, they have to overcome the intermolecular forces. During condensation, the intermolecular forces hold them. So that's the difference. And we're going to talk on the next recording about the energy involved in that process. So condensation is nothing more than the opposite of vaporization, and you can explain it thinking about intermolecular forces. So with all that said, go back to it if you have to re-listen to it again. Try to explain this. Acetone evaporates more quickly than water at room temperature. What can you say about the relative strength of the intermolecular forces? Put together everything that we discussed and see if you can figure that one out using all those concepts. Which substance is more volatile? Volatile means evaporates easier. So easier to evaporate. So for example, gasoline is more volatile than water because I cannot smell water, but I can smell gasoline because the molecules are escaping and they reach in my nose. My nose, sorry. Remember, I told you at the beginning of this chapter, this theory that we have been learning through all these chapters, now we can put it together to understand everything that's happening around you. Why does gasoline stink? Intermolecular forces are so and so and so, therefore the molecules can get to my nose and I can sense them. Why water doesn't smell? Think about the intermolecular forces. How come water molecules don't get to my nose? And everything will make sense around you. Once you're done with that one, then try to explain this one. How come when your body sweats, why do you feel cooler? Remember, we talk about vaporization and we also talk about condensation. And then close with this one. Explain why a steam burn from gaseous water at 100 degrees, so it's water at its boiling point, is a lot worse, so the steam is a lot worse than just water at 100 degrees Celsius. So we're talking about liquid water at 100 degrees Celsius, steam or vapor at 100 degrees Celsius, and vapor will burn you a lot more. It will put you in the hospital. Why? And when you do all that, and send me questions if you need to, hopefully you will have a better understanding of evaporation and condensation process. So when we come back, we're gonna see everything that we just talked about it, but we're gonna do that by putting numbers to it and actually calculating based on the mass the energy that we expect to be involved in that process of vaporization. And then we will do it also with freezing and melting. So until the next one, I will see you soon. Continue working with evaporation and condensation.